Let us look at the structure of the stack in old kernels. So, as we have said before, the size of a stack is limited to 8 kilobytes. So, kindly note that B will be a capital because it is bytes. So, this is 2 pages. So, the thread info structure is stored at the bottom of the stack. I'm sorry, this arrow will be like this. Okay, so now coming back, the thread info structure is stored at the bottom of the stack. And we need to understand why this is the case, right? What advantage do we derive by this? So the key point is that the current pointer should be available all the time because this is something that we read very frequently. And hence, we want to spend as few instructions as possible in reading it. So, where do we store it? Well, it's hard. It's not possible to store it in a register. We want to spend a minimum number of instructions in kind of calculating its address. So one easy way is that we come to the bottom of the stack very quickly. We find that the first 4 bytes contain the current pointer, and basically we from there the current pointer essentially is a pointer to the task struct. So we can go to the task struct from there. So this turns out can be done efficiently. So the stack frame is aligned to 8 KB stack boundaries. So basically, a stack boundary is nothing but a multiple of 8192 bytes, right? So that is what a stack boundary is. That it's basically an address which is a multiple of 8192 bytes. So this is we will use this, right? So basically, given the stack pointer, whatever it is, so let's say this is the current value of ESP. It turns out that within one instruction, we can find this address. So how do we find it? Let me first explain with a simple example. So let's say the size of the stack is 100 bytes. And given any ESP, we want to find the size of the stack. We want to find the pointer to the bottom of the stack. So if let's say the ESP's value is 756, then we can happily say it is the pointer to the bottom is 700, right? Why is this the case? Because memory addresses increase this way and the stack is aligned to 100 byte boundary. So what did we do? We basically replaced the two lower digits with zeros. So we can do the same in a binary world. So it turns out that 8 KB is 2 raised to power 13 or 8192 bytes. So what we do is given the value in ESP, so it's represented as percentage ESP actually. We need to AND it with some quantity such that the bottom 13 bits remain. Sorry, the bottom 13 bits become 0 and the rest remain. So that's not very hard. So basically, what we need to do is that if we sort of write down from the left side, it will be 000, again 000, again 000, and then there'll be 0 and then 111, right? And everything to the left is all ones. So given the sign extension trick, which all of us have studied in computer architecture, we can AND it with this value in hex, which is 0x. This is 14, so this actually stands for E, and this is 0 and 0. So if we basically AND the value of ESP with this constant over here, then the bottom 13 bits will become a 0 and will immediately come to the bottom of the stack. Now, if we read the pointer that is stored here, right? then we will get a pointer to the task struct. So basically, computing the address of task struct essentially becomes an AND operation with a constant, then a load operation, right? And so this math over here should be clear from the decimal example. So this is all that we need to do, which is a neat trick for finding the address of the current pointer. So we have a load, but hopefully the load will come from the cache. So the load will be reasonably fast. So in the current kernel, things happen slightly differently. So what we do is that define the current macro, which is nothing but a call to the get current function. The get current function is basically an inline function which returns struct task struct star, which is a pointer. And the inline function essentially reads a per CPU memory region. And so basically the current task is passed to it and it's populated and it comes back. So it turns out that this can be, this is translatable to a single instruction. And we'll see how that works. But the key idea is that we are defining a per CPU storage area. All right. So that is a trick. So in this case, it turns out with only one load instruction, we can get the value of current. As opposed to two instructions earlier, we can do it with one. So the current task is pretty much a global variable stored in memory. This CPU reads table macro. This reads the task struct pointer from a separate per CPU area, right? I mean, per CPU, let's call it memory area. So in some architectures, of course, this could redirect through the thread infrastructure, but not here, right? So the key point is that we don't have the function call overhead because we have this always inline directive, which basically says that we don't have a call or a return, but the code of the function is directly pasted into the callee's code. I'm sorry, the caller's code. So whenever you're calling a function, you don't call and return, but whatever code is there, that is directly pasted. So what did we learn from this part? The current task struct is something that needs to be accessed very quickly and very frequently. So where do we store it or where can we not store it? We have limited registers. So we cannot really store it in a register. It will just eat up one register. Again, we can't store it in a global variable. It needs to be CPU specific. Right? So global variables in a shared address space are not CPU specific, but this has to be. So then, what else can we do? We can, of course, go to the bottom of the stack the way we did, and then use an additional instruction to compute the address of the pointer. Uh, Doable. Store a pointer to it in a model specific register. Again, doable, but we need to have such registers in our CPU. That is sometimes the case, sometimes not the case. So on x86 machines, the best that designers have thought of is to store the pointer in the local storage area of a CPU, and the segmentation mechanism makes it kind of easy to go for this. Where the local storage area on the CPU is accessible, and there all of these pointers for current task struct etc. can be stored. So what is actually used? So what we do is we store all CPU specific variables in segmented memory. The GS segment register and the segment registers are CPU private. So they can very easily be used to point to per CPU memory regions. So all that is needed is that we need to access a memory operand of the form percentage %gs. Then of course some displacement, scale index space. So the advantage here is that we can within one instruction load any value that is stored in the GS segment, and this segment is private to a CPU. It's a private memory region. So the current pointer is stored here. It can be retrieved. So we'll find that Linux uses the GS segment for other things as well, and it uses a few other user defined segments for storing CPU local information. So of course you have a declare per CPU, define per CPU macro defined in per CPU.h that does this. So the advantage of defining CPU private data is that unlike shared data, it does not migrate or bounce around between cores or processors, and it just remains with the CPU. It's not accessed by other CPUs, so it does not have to go to their caches. Undeniably leads to a higher performance because of this issue. So now we will discuss priorities. So priorities are important mainly because they are used by the scheduler for scheduling, in the sense that if a process has a higher priority, it gets more CPU time. Linux divides the priorities into two types: real time priorities and user priorities. Total there are 140 priorities numbered from 0 to 139. The real time process priorities, which are those mission critical, highly critical processes, its priorities are from 0 to 99. The priorities for user processes are from 100 to 139, and this is for user process. So clearly user priorities and real time priorities are very different, and in this case so we'll also look at how to interpret these numbers. It's quite tricky. So these are the numbers that the OS uses for assigning priorities, but the way that the scheduler interprets them is quite different. So the way we interpret them is like this: for real time processes, higher the priority value, higher the number, higher is the actual priority. So this means that the task with priority 99 has the highest priority in the system, right? Even though I would advise nobody to set the priority that high, it makes the system unstable, but this is the way it is. For regular processes, on the other hand, the default priority is 120. Here the sense is different. So lower the number, lower the value, higher is the priority. In this case, higher the number, higher was the priority. In this case, lower the number, higher the priority. So basically, if let's say if this is the priority and this is the number, in this case, the highest priority would be when it is 100 and come down when it is 139. So the task with priority 139, where the number is 139, has the lowest priority, and among user processes, if the number is 100, it has the highest. There is a way for a user process to change its priority either before running a command or in the middle of a process's execution. All that we need to do, let's say at the beginning, right? Nice is one command, chrt is the other, is to nice minus n the nice value and the command. So in general, for non-super user processes, the nice value is positive. The priority ends up becoming 120 plus the nice value, right? That is what the priority ends up becoming. So nice basically means being nice to the other process. So in a sense, by increasing our number, we are reducing our priority, and reducing our priority kind of makes us fall to the background and others kind of get a higher CPU time. However, if I'm the super user, right, then things are somewhat different. Then the priority, the nice value can be negative. So you can't make it a real time process, but it can go till -20 in the sense it can become +100, which is the highest priority for user processes. So that can be done. So the priority can be set to 120 plus the nice value, whatever it is, right? And as I said, for user processes, the nice value is positive, and for the super user, it could be positive or negative. But it's important to remember the sense of real-time processes is like this, and the sense for regular is like that. Relevant kernel code in kernel shared core.c. Again, if it's a real-time process, the number that we derive is max RT prio, which is 100, minus 1 minus the priority number. So essentially, if my number is 99, then prio is basically 0. And if my number is 0, then prio is 99. But at least in this case, this has the highest priority. Okay. By far, this has the highest priority. And for regular processes, we call nice to prio. Nice to prio just adds 120 and the nice value and returns prio. So in this case also, basically lower the value of prio, higher the priority. And this will start from 100 to 139. And you can see the pattern. So first 0 to 99 have the highest, in terms of prio values, the highest priorities, and then 100 to 139. So it makes the sense the same. The sense of the numbers. So lower the value of prio, higher is the actual priority. So the scheduler, what it does is that it typically has different queues for different priority values. So what it would do is, let's say for priority 50, it would have one queue of tasks, that is. Then say for 51, one more. And it will choose tasks from these queues depending upon its scheduling policy, which we will discuss in great detail later. Next, coming to shared info. So shared info is again some information that the scheduler uses along with priorities. This is simple bookkeeping stuff, so I'm not discussing a lot about it. Simple things like number of times that a task has run on the current CPU, time spent waiting in the run queue. So what is a run queue? It's basically a per CPU. We have a run queue, which is all the tasks that are ready to run on the CPU, right in the running state. That's the run queue. Then furthermore, other information, when did we last run on a CPU? When were you last queued to run? and a few more, but you get the pattern. Is basically like a history, right? It's like a past history, and that will be used to determine the scheduling of this task. And clearly, fairness for us is an objective. So, with the priority and the shared info part, the scheduling part should be clear. So, now we will go to MMstruct, which is a very, very important data structure for many reasons. It is basically, it represents the virtual address space. It contains all the information that is related to the memory usage of the process and describes its virtual address space. Pretty much it controls it. So the key components are a maple tree, which is nothing but a variant of a standard B tree, right? So the B tree, if someone doesn't know, this is a good time to pick up. So this stores a list of all the virtual memory regions that this process controls. Then other metadata: size of the VM space, the number of VM regions, and other smaller statistics like the total number of VM pages, the locked VM pages, pinned pages, and so on. The page is set to be pinned. Pinned basically means that it is kept in main memory and it's not allowed to be evicted. So the kernel cannot flush it to the hard disk. Then we have start and end of memory regions. So basically, there are some memory regions which are specifically important, like the code section. So it's start and end of the data section, and start and end of the stack section. Modern kernels don't really use these, but still it's there. And then a pointer to the owner process, the struct task struct star owner, and the CPUs that the current process has executed on. So this is like a history, but there's an advantage to this. Say the current process would like to be migrated to some other CPU. You would ideally like to go to a CPU on which it has executed on in the past. And the reason for that is that its caches will be warm with some of the processor's data. So basically, you will find the data kind of close to you. That is why you keep this information with you. So now let's now see what does a virtual memory region look like, and how do we actually reconcile that with this. So virtual memory region is represented by VM area struct. So if you look at the virtual address space of a process, which can theoretically be between 0 and 2 raised to power 64 minus 1, uh, some part of it is occupied here at the top, the stack. Some of it in the middle, the memory mapped areas, and that too not necessarily contiguously. Then the heap, of course, and then the code and data. So, and in large parts of the map are sparse, very sparse. So we need to store these regions where every region has a start and an end, right? A VM start and a VM end. So pretty much what we are storing is that we are storing intervals. That's the primary thing that we are storing in a VM area struct, along with a back pointer to the parent MMstruct object. And we are steering two more things which we will discuss later, but I just want to give a sneak peek. The first is that there are two kinds of virtual memory regions. The first part is called anonymous virtual memory. So in this case, if we are kind of using the malloc call or new call to, let's say, allocate an object, then that would be anonymous memory because it didn't exist and we just created it programmatically. This is as opposed to, so incidentally, we store these in a linked list, right? We will describe later why. And a VM area region could also be mapping the contents of a file, where a file is nothing but an array of bytes stored in disk, the hard disk or flash drives. So basically, the file itself could be mapped to the virtual address space, and the file could also be a shared library and executable, anything. So once that is mapped, there is a backing store. The backing store is the file, right? So that is called non-anonymous virtual memory, and we still keep a pointer to the file that has kind of produced this virtual memory mapping, right? And so that is why we have a pointer to it. So these are the four broad fields of this VM area struct attribute. So now let's come back to the maple tree and how exactly is a maple tree connected to a VM area struct. So the VM area struct, we'll refer to it as a VMA or a virtual memory area. So a VMA basically is an interval. We have a start and an end. So of course we will need a structure to store these intervals. So we need the insert operation, we need the delete operation, insert an interval, delete an interval. Also maybe another operation to check if there are overlaps. If we are inserting an interval, it should not overlap with any other interval. But the most important, one of the most important, I would say, is given an address, we search which interval it lies in. So we need a data structure to manage that, and hashes are not really the best, particularly for the search operation. So to locate and manage these VM regions, we use a maple tree. And as the maple leaf suggests, uh, we have every node has multiple children. The nodes are reasonably wide. We'll see what that means. And there are many levels. So the maple tree is meant to precisely solve these problems. It keeps a track of VM regions. It's an insert delete search structure, and it's very important in this case. So previously, what is a contender that maple tree is replacing? So the incumbent was the red black tree. So the red black tree was used. So it was a balanced tree, uh, mostly balanced binary tree. That was not a good idea. People didn't like it. So the B tree B tree came, which is also balanced, by the way, but it's scary and it's fast. So we'll see it's roughly 40 to 50% faster, and the maple tree is even faster, even though the maple tree is a variant of the B tree. And there are many other advantages of this structure, in the sense we can iteratively kind of go through them, right? We can iteratively go through the intervals, which is not possible otherwise. So hashes, etc., could have done the job, but traversing them in a sorted order and doing these search operations like this is somewhat difficult. Hence, hashes were never really serious contenders. Red black trees were, because they are balanced. But B trees, as we shall see over here, they have an advantage. So a B tree has an order. So if let's say it's a B tree of order k, every node, internal nodes, that is, you have internal nodes and then you have these singletons called leaves. So at the bottom we have leaves. So the internal nodes are at least half full, which means they contain greater than equal to k by 2 entries. Where, let me tell you what an entry is with an example. So let's say I have two entries, 6 and 12. So all the subtree to the left of 6 contains everything that is less than equal to 6. Then the subtree between 6 and 12 contains everything which is greater than 6 and which is less than equal to 12. and the subtree to the right of 12 uh, contains everything which is greater than 12. So of course, there is a fair amount of disagreement with regards to which variant of the B tree is authentic, because there are so many variants. So some schools of thought say that, look, the value should only be at the leaves. Some schools, so that would be more like a B plus tree, but others say that a value can be there anywhere, right? Wherever you find it, the value is there. So that is more like a B tree kind of thinking. So we will go with a B tree because that's what a maple tree is, with restrictions. Then in 2 and 4, anything less than 2, like 1 is less than 2, it appears here. Between 2 and 4, 3 is between them, it appears here. 5 is greater than 4, so it appears here. Same is the case for, as you can see, 7, 9, 11, and 14, right, less than 16, 17 between 16 and 25, and 26 more than 25, right? So basically, if we have L values in each internal node, we'll pretty much have L plus 1 children. That's the idea. But the good thing is that this is balanced, in the sense, if I insert something, then basically this node will split, right? And it's this half full criterion will still hold. But this node will split, and then we can add these values. If we can't add them further, we'll then send something to the parent. The parent might split, so on and so forth. But the tree will always remain balanced. And all operations hence will always happen in order of log n time, which is insert, search, delete, etc. So this is the advantage of a B tree over a red black tree, which is that it can contain a kind of a range of values, and it's easy to find which subtree you need to go to. And to a large extent, because we are allowing a node to have a lot of children, the need for rebalancing is low. So there is a sufficient amount of slack in the tree to avoid frequent rebalancing, because rebalancing frequently is a pain. So basically, that's why the B tree is considered a reasonably scalable and flexible structure, which, while remaining balanced, can provide great performance. So the maple tree is a range based B tree where we store a range. And so, of course, we can store the starting address as the search key pretty much in the B tree. So all of these are, by the way, they derive inspiration from the founding father, the binary search tree. But the search key could be the beginning, the starting element. And then, of course, you could resolve the tie, kind of, if you're the end could be used to figure out when an interval ends and so on. But pretty much the starting element could be the search tree. What makes a maple tree and not a B tree is that it's a B tree, no doubt, but with strict caveats, that the branching factor, which is the number of branches, is 10 for non-leaf nodes and 16 for leaf nodes. So this kind of a maximum figure, and also a recommended figure at the same time, in the sense that you may have nodes with less leaves than this, but you would strive to make it 16 and strive to make it 10 for non-leaf nodes. Furthermore, the node size is 256 bytes, which is a good thing, because it's a multiple of the cache line size, right? So that is important, that if a cache line is 64 bytes, then it's pretty much 4 cache lines, right? And so then managing this becomes very easy. If it's like 2 cache lines or 4 cache lines, then managing them in the cache is very easy, and you can very nicely predict how, let's say, an L1 cache can fit how many nodes, and how do we need to kind of organize the full thing. So because of its nice interaction with the cache also, so there are other advantages as well. So given the fact that we have a large tree, Different processes could work on different parts of the tree at the same time, even if they are making invasive changes that won't really matter. Furthermore, if let's say different processes are just searching, that would be a read only access. That also can be done in parallel, right? So uh, the thing is that even if the processes are reading, they don't have to be isolated from each other. Even though when they are writing, we would like to minimize their overlap. So that said and done, this becomes a fairly effective structure for managing these virtual memory regions as opposed to the nearest competition, which is of course red black trees. I won't count hashing as a strong competitor, but even binary search trees to my mind is a strong competitor, but BSTs are not balanced. But then there are balanced versions of BSTs, which would be these red black trees and AVL trees and so on. So let's end this part with a recapitulation of what is anonymous and non anonymous virtual memory. So, on a storage device like a hard drive or a flash drive, a continuous array of bytes is called a file, right? So, it is a contiguous array of bytes. Uh, so, what happens is that accessing these devices, the hard drive or the flash drive, they are very slow. So, a lot of files that need to that exist over there are very useful when it comes to running a process, particularly the executable, the binary, which contains the code, the machine code, and the data, and the shared libraries, which again come with that code and data. So, what happens is that we take these files and we map them to the virtual address space. So, parts of the virtual address space, as we have seen with the case of dynamic loading, that parts of them are mapped to files. So, then other files can also be mapped to the virtual memory space. So this would be non-anonymous memory because the memory is being backed up with a file, right? The contents are coming from a file. So this is the reverse of anonymous memory or anonymous VM regions that comprise parts of the heap that we create, the program dynamically creates using the malloc and new calls, right? Using malloc and new, these are regions that the program dynamically creates and we subsequently use. So what happens is that for allocating objects, we say that dynamically I create a 10 KB region for storing objects, and then I can tear down the region, so on and so forth, several times during the course of the execution of a program. So such regions which are created kind of impromptu by the program are called anonymous VM regions. So this finishes our discussion of the scheduling aspect and the memory management aspect. So we will now understand a few more intricacies of the system, notably the process ID. And the process ID is a unique number that is assigned to each process. So as we have discussed earlier, we can't use int, char and so on because we don't know how many bytes it is on different systems. Hence, to provide consistency, we define our own types. So PID underscore T is a type of PID, which is an unsigned number, unsigned integer. But we need to define it because we'll use this code on all architectures. So before we proceed forward, it is necessary to understand one more data structure called the Radix tree because we'll use it quite a bit in this section. And then only we will go forward. So the earlier data structure maple tree was in a sense more suitable for uniformly sparse data. But this data structure is more suitable for data that is somewhat related. So I'll show an example. So let's say the strings are travel, truck, tram, trust, trick, trist, tread, tractor. So you see that the strings are somewhat related. So if I want to have a data structure for the same insert, search, delete, then and let's say I want to search truck, I look at the first syllable, I find it here. I look at the second syllable, which is R, I find it here. The TR I find here. Then I find the child that has U there. So this becomes TRU. And finally, we have TRUCK. So TRUCK is basically a path in the Radix tree. Similarly, if I want to do Trist, Trist would be TRYST, which is again one more path in the Radix tree. As you can see, these English words are in a sense related. So they have some relation to each other in terms of the starting symbols being similar. That is why we can quickly uh, traverse this tree, and it's a nice and compact representation for storing all this data. Of course, you may say that is it easy to insert something? Well, it is. So of course, if it doesn't begin with tr, then we can add a dummy node and then add one more node. If let's say sorry, that begins with a d, and then we could do that. Or if you want to, let's say, introduce uh, trite, trite, so then we could do that like this. Deletion is also easy, and searching is easy. It's an easy data structure to manage. Its natural competitors are hash tables. So basically, hashing based solutions are like this, that we have to read the entire string and mangle the bits. So the time it takes to do the hashing, right? That time is a lot. I mean, can be a lot, because a lot of bits have to be read and mangled and everything. So basically, what needs to be done is that we have to move away from hashing, because that is slow, and instead the complexity of this is not much. It's just a single pass over the word, and this you would anyway do in any hashing based thing, which is to read the word and then mangle the bits. But that may involve multiple passes, and it actually does involve many passes, 10 or 15 passes. But in this case, a single pass over the bits and a single traversal over the tree will take us to the node. This is why the radix tree is good for organizing information that has a related structure, as we can see here, right? At least a prefix, a large enough prefix in common. And when are prefixes in common? Well, when we are basically, let's say, counting something like PIDs, okay? So essentially 00001, and then 00010, and so on. So in that case, as you can see in these numbers, while counting, the prefixes are common, and because of that, it is easy to use a radix tree in this context. So the process ID or the PID is like this, that every process is uniquely identified by an integer, and that integer is called a PID, and this integer is used by other system calls and the kernel itself to identify the process, right? So a process is basically identified by the PID number. Furthermore, processes can be a part of a group. So this is known as a process group or a thread group. So where we will have a bunch of processes. So every group has a thread group ID. A bunch of processes will have a TG ID or a thread group ID. All the threads in the group will have the same TG ID. Well, they have to have, otherwise, how do you figure out that they are a part of the same thread group? So this is typically equal to the PID of the main thread. So every thread group will have multiple threads, where every thread is a process in its own right. So every thread has its own PID. One of them will be the main thread. So let's say that the threads have PIDs, 30, 40, 50, and 60, where this is the main thread. Then the thread group ID will be the PID of the main thread, which is equal to 30. So this, in a certain sense, will help us simplify the process of creating the TGID and managing it and mapping it to something that is realistic. So this is where there's a little bit of a problem, in my view, in the Linux kernel, that it also uses a PID structure, right? A struct PID, which is not a number, even though the name is shared, and that's the problem. This leads to a lot of confusion. So PID also refers to a process. The struct PID structure, also refers to a process. This process could be alive or it could have exited, and its PID number value, this reused. So, which could have been like long dead, but if you still want to refer to it, the struct PID can be used, right? So it also contains other bookkeeping information. So the struct PID is also used along with the integer PID, right? Both refer to the same process, but as we shall see, the structure is slightly more intricate than that. So we run the command ps minus ls. If you run that, you can see all the processes in the system along with the, it'll tell you which thread group they are a part of, what is the thread group ID, so on and so forth. So how are these PIDs managed? So Linux exposes something called the /proc file system. The /proc file system is a special file system in the sense it is used by the kernel to communicate with user processes in a one-way fashion. In the sense, kernel is like a display board, some sort of a bulletin board of a kernel, where it will show you different aspects of its execution. So in sys kernel, the file PID max, it contains the maximum number of possible PIDs. The default is this, which is 32,768, same as 2 raised to power 15. So this is a total number of processes that you can support. But the bigger question is, how do you manage these processes, in the sense the typical operations? Have to be supported, in the sense search if a given PID is mapped to a process, right? And which process it is mapped to. So this basic search operation. Insert would be to create a new process, and delete would be to kill the process. So the question is, how do we manage the list of PIDs? That itself is complex. And what about the PIDs? List of PIDs would include two things, given the fact that we would like to reinterpret the numbers and the PID structures, right? So both are kind of complex. Of course, if we want to create a new process, we need to find a free PID number, and that to find it quickly, and it should be kind of unallocated. All these things three things go hand in hand. So before we discuss, this is a complex problem, as I said, so there'll be many answers, nuanced answers, or what they call layered answers, answer sub problem by sub problem. So we will, in a sense, attempt to do that. So overall, what we will do is that we will divide the set of all the processes into namespaces. So if these are all the processes in the system, we will divide them into namespaces. So these are disjoint namespaces, right? Uh, well, but again, this disjoint thing we will want to look at later. But a namespace is a set of processes that can only see each other, right? So the processes are only mutually visible to each other, and they are not visible to other processes. So namespace is such a closed entity. So the idea with a namespaces is that they naturally lead to the notion of containers, where a container is nothing but a container of processes. And for them, this is an isolated world. They only see each other and they only see the resources that the parent OS has made available to the container, which means that every container will have its own process space. Needless to say, memory space associated with the processes. You clearly cannot share memory across containers and the file system. So every container will have its own private file system. So the file system and memory part we will look at later. But the process space or the space of processes in a container is nothing but a namespace. And namespaces themselves have a hierarchical organization. So you have a parent namespace, a child namespace, so on and so forth. And any process that is a part of, let's say, this namespace is automatically a part of all the parent namespaces as well. Not the other way, but it is a part of all the parent namespaces. So a container in itself can be, you can do beautiful things with it. It can be suspended, which means that all the processes within the container, everything within it, right? All the processes, all of them can be paused. They can be later on resumed, and the container itself, right? So a container of processes itself can be migrated to another machine. And the processes will not get to know, you'll just pause them here and resume them there. And given the fact that the processes will continue to have the same PID numbers and will continue to see the same resources, they will not perceive the difference. So this is, the overall idea of containers, which has pretty much led to the cloud computing boom. But the key idea or what enables these containers, a part of the technology, is the idea of namespaces, especially hierarchical namespaces, where a process that is a part of a child namespace is also a part of all the ancestral namespaces as well. So let's look at the PID namespace structure. So we have a Radix tree. With every namespace, we have a Radix tree. An IDR is nothing but a Radix tree. So this does an interesting mapping. It does a mapping from the PID name, I'm sorry, the PID number to the struct PID, right? Rather a point to a struct PID star, a pointer to a struct PID. So what it does is that given the ID of a process, it establishes a mapping between the ID of a process and the struct PID star. And this is crucial, this is critical. So this is what maintains the indexing of the namespace. Another important idea in software development is the idea of a pool. So KMM cache is nothing but a pool in the Linux kernel, but a pool is a much broader concept. So in general, when I want to create a new object, I use either malloc, and malloc's the thing is the number of bytes, or I use new. So I say new means create a new instance of an object. Within the kernel, of course, I can't use these, but what I can use is rather kmalloc, which is kernel malloc. And later on, I free the region with kfree. So the point is, a malloc and free are both they're user level calls, even in the user space, and kernel level calls in the kernel space. But they are very slow. They're very slow. They are very time consuming, and they are very non-deterministic in nature. So basically, because of these problems with kmalloc and kfree, what we do, or rather we prefer to do, is that we have a pool of allocated objects. Whenever we want to create a new instance of an object, we basically fetch a pre-allocated object from the pool, and then its fields are appropriately reinitialized. So this is a very fast operation, right? Much faster than kmalloc. It is deterministic in terms of timing, and the probability that you will always find an object can be made abysmally small, can be made very small, in the sense that you can analyze and kind of analytically say that at the most I will have these many objects in the pool, not more than that. So because of the because of such high level logic, it is possible to ensure that whenever you want an object from the pool, you will get it, and once you are done with it, you return it back to the pool. And if your system is well understood and well analyzed, it should never be the case that you actually run out of objects. It's much faster. So we have a pool of this type, a kmem cache, a memory cache, kernel memory cache, which contains objects of type struct PID. So this is where we would like to use it to fetch an instance of an object. The level is kind of straightforward. It is basically the level of the namespace, in the sense the root namespace. Let's say we'll have level 1, and then level 2, 3, 4, 5, and so on. Every namespace has a parent. So because we have a hierarchical namespace system, so every namespace has a parent that has a parent, so on and so forth. And it has a level as well, which we also saw. So the Radix tree in a namespace basically stores a PID structure. So for a single process, the struct PID is the same, albeit it could be stored in different namespaces. Where this is a child of that. So originally, it could have been created by this namespace. So its level will be set equal to 4, because the level of this namespace is 4. And we will discuss these two later. So even though the struct PID is the same, if you see, each namespace has its own private Radix tree. In the Radix tree, what happens is that the PID number is different. So the PID number, right, not the structure, but the number. So for each namespace, right, the PID number is different. In the sense that the same process, right, so with the same struct PID, could have a number 30 here, 20 here, 40 here, 50 here, and so on. So the numbers are different. So that needs to be understood. In general, we will not have a hierarchical namespace system. We'll have a single namespace, hence the struct UPID, which is nothing but just a tuple of the PID number and the namespace, right? Just a tuple, right? Of the number of the PID in that namespace. You'll only have one, because it will be a flat namespace without containers. But this array can be dynamically resized in the sense it can be made larger. For example, in this case, if there is nesting of four, so so as you can see, there are it has three ancestors, right? Or let's say the root has three descendants. So this can be dynamically resized, and you can make an array of four entries, where every entry will have a pointer to the namespace that it corresponds to, and the number of the process in that namespace. So you will now argue that why is this int nr, why not PIDT? Well, that that decision is better left to the designers of Linux, right? I would have preferred PIDT instead, but anyway, that's what they have done. So this is the broad idea, that we have radix trees in each namespace. The PID number is different, but the struct PID is the same. The struct PID star, the pointer is the same. And furthermore, we can have groups of processes, not just one process, but a group. So processes are grouped when they are different threads, so we form a thread group. Or you can create also what is called a session, which is essentially a group of processes, again grouped together. We'll discuss these ideas later, but the key idea of a ref count and this tasks linked list, right? Struct hlist head is a way of defining linked lists in Linux, a doubly linked list, because almost all linked lists are doubly linked lists. So in this case, this is saying that there could be a list of tasks that use or refer to this PID, in the sense that they could all be the tasks same as processes in the group, the thread group, or in the session, right? So this is basically how many of them are referring to your current PID, and the ref count is something similar. It captures a similar sentiment. So this is the broad idea of the hierarchical namespaces, the idea of having a single struct PID for a process and having different numbers for the same process, right? Different PID numbers for the same process across namespaces, where this mapping in the namespace is held together by Radix tree. And why a Radix tree? Because these are basically the numbers which are incremented. So there is a basic structure in terms of the prefixes being mostly the same. So let's go forward. So allocating a PID structure. So this is crucial. So we call the alloc PID function defined in kernel PID.c. The first thing that it would do is it would access the pool, the KMM cache, the PID underscore cache p entry, which we saw here, here to be specific, is the one that is accessed. So you fetch an entry from the software cache and reinitialize it to make it a PID structure. Given the fact that you may be a part of many namespaces, allocate a PID number in each ancestor namespace. At each level, add the PID structure with the PID number, of course, to the Radix tree at each level, right? So you're adding, the key is the PID number, let's call it PIDT, and the value is the struct PID star, right? So that's what you get back. How do you use a Radix tree here, and what's the idea? So the idea is that we store all the processes in a Radix tree, right, per namespace. The key is the process ID, as we have said, and the value is the pointer to the PID structure. Works like a hash table, but as we have argued, computing the hash and dealing with linear probing or double hashing or chaining issues is tough. That is why hash tables are hard to use in practice, and the Radix tree is better. Now the question is, how do you find a free entry? So this is where there's a logical break in our thinking. We'll take a digression and join back later. So let's say we are allocating a new process. Then the question is that how do we find a free PID, a free PID number, right? How is this to be found out? That is the question. So let us restart our discussion from this point, which is that how do you find if a given process ID, let's say process ID 1000, is it free or not, right? Or is another process mapped to 1000? So that's an important question. So let us kind of forget about the Radix tree part. We'll now go in a different direction, and finally, we'll go in a different direction, and both the directions will ultimately converge. But we are at this point where we are taking a digression. So what we will do is that we'll maintain a bitmap. A bitmap is essentially an array of bits, right? So basically, if we have 32,758 processes, as you can see, sorry, 768 processes, as you can see over here, then we will have 32,768 processes, sorry, bits over here. And the kth bit would essentially indicate if the kth process ID or process ID k, is it free or not? If it's free, you'll have 1, otherwise you'll have 0. So essentially the problem of setting and resetting, which is that saying that look, a given PID which is k has been taken, is very easy. You just go to that location and set it to 0. And when it is free, you set it back to 1. Setting, resetting is easy. But let's say given this location and assume it is not free, then going right and scanning and finding the next free entry, the next one, this is difficult. So we need a different data structure for it. So we'll introduce a different data structure, then we will kind of try to converge, even though I will not take you fully there because the details are somewhat complicated, but you'll get the broad idea. And the idea is, given the first index, find if the next index is free. So a simple idea could be that we break this into chunks of 64 bits. So in a sense, the kernel code does, it does that. So this bitmap is represented with xarray.h. So xarray.h has the data structure. So even the smaller chunks, which we are seeing is basically 64 bits long, right, will also be, instances of xarray. So what Linux does is it processes the entire bitmap, 64 bits by 64 bits or long word by long word. So thankfully x86 has an instruction called BSF, which given a long word, which is a given a 64-bit register, can actually find the index of the first one wherever it is, right? Yeah, so basically wherever it is, the first one is there, it will find the index, or it will say that, look, I didn't find the index, right? So there is no one here. So you can find the function, you can see, look at the function radix tree find next bit in /lib/radixtree.c. But essentially the big broad idea or the key idea over here is that we would we are kind of going fast. We are not going bit by bit, but we are going 64 bits by 64 bits. So that itself is fast, and we're using a fast hardware instruction to process all 64 bits in parallel, right? Somewhat in parallel, I mean, very quickly. So this process can be accelerated. So let's look at the computational complexity of this. So this technically is order n because you may have to scan the entire array. You want to make order n order log n, just for a theoretical purpose. So we can use a data structure called a van MD tree. So as I've said, we have now diverged from the Radix tree, but we'll again converge. So the idea of the van MD tree is basically that you have one node that covers two children, contiguous locations. And this is basically free, this is not free. And the internal node says whether this entire subtree has a free node or not. So it clearly does. Hence, this is 1. Similarly, this is 1, but this is 0 because the entire subtree rooted at this node does not have a free node, right? So basically, this is the internal node's value here is 0 because the subtree doesn't have a free entry. But again, the internal node's value here is 1 because this subtree has a free entry like this. So on and so forth until the root. So the root essentially indicates whether the entire bitmap has a free entry or not. And then you can traverse it to find it. So if I want to find the first free entry, I start at the root. I have a preference towards going left, right? As long as I find free entries. So then I go left, 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 and I find it here. If let's say this was 0 and this was 1, I would go left, left, left. This I would not find to be free, but I would record this as free. Now let's say that, let's maybe convert, okay, let's this be 0, but let's convert this to 1. So what will happen is that I'm just doing some conversion. This is 0, right? So I'll just write them once again, 0, 0, 0, 1. So this will get converted to 0. This will get converted to 1. So let's say that we want to find the first location after this location, which is a 1. So I go one level up and I see that its value is 0, which basically means that the subtree has nothing. So I go one level up. I see that this subtree is saying that there is one element which has a value 1. So since it's not the left subtree, it must be the right one. So I go right. And here again, I scan the children. So I find that there is no hope here, but there is hope here. And I'm able to find an entry that is 1. So what you can see is that I am taking log n steps up, doing constant amount of work per step, and taking log n steps down. So my total work is essentially a multiple of log n. So the time it is taking is order log n time. Of course, this makes us happy as students of algorithms and data structures. But in terms of efficiency, it turns out that this algorithm here, which is traverse it long word by long word and use the machine instruction, can be married with this. So what we can do is that we can store multiple bits in each leaf node and internal node. So let's look at leaf nodes. So what we can do is we can take a large bitmap, divide it into chunks, and assign each chunk to a leaf, right? So basically, within a leaf node, we can use this algorithm to traverse it word by word and basically find the location of the first one. And the subtrees could indicate the same information, whether the internal nodes could indicate whether the subtree has a 1 or not. And of course, we can fine tune the information. We can say which child to go to and so on and so forth. But the key idea is that we can combine the advantages of the word by word algorithm with this. Instead of proceeding bit by bit, each entry of the leaf could actually contain multiple bits that will make the process more efficient, right? It will reduce the height of this tree and make the process more efficient, because in a computer architecture, we really don't process data bitwise. We actually process the data at a higher granularity, at least 4 bytes, 8 bytes. In fact, more if you consider cache lines, but definitely not bitwise. So now it's the time to converge. So why did we discuss two things? We discussed a radix tree whose job was to map a PID T to a struct PID. That was its job. And then we discussed a Van MDBOS tree, call it a VEB tree, to basically manage the kind of the PID-T bitmap. So what Linux does is that it actually combines both of them, and in a sense, the Radix tree subsumes this. How does it do that? Well, the leaves of the Radix tree contain chunks of the bitmap. So they contain X array instances, which is nothing but chunks of the bitmaps. And the internal nodes contain the exact same information that is contained over here. So what happens is that within, let's say, a leaf node, we traverse it, long word by long word, as is written over here. And then the data is kind of divided. So if it's a radix tree, and let's say the tree looks like this, right? And so the data, the entire bitmap is divided into chunks among the nodes of the radix tree, let's say the leaves. And the internal nodes are augmented with information regarding the free fields that are there in the subtree rooted at that internal node. In a certain sense, the radix tree nodes are enhanced with additional information such that it functions as a Van Emde tree as well and helps you quickly locate free PIDs and so on. So the Radix tree is playing a dual role, which is the mapping of the PID tree to the struct and also finding free PID entries by also including a part of the PID bitmap. So of course the implementation can be seen. So it's actually idr.c, and the implementation of the Radix tree, right, can definitely be seen in the kernel code. So if I just go back to the relevant code, so the struct IDR is what contains both. So the code is incredibly complex, but if someone wants to go and look at the code, I won't discourage the person at all. And then now let's finish the task struct, right? And look at the file system, IO, synchronization, and debugging related fields. So we'll discuss files and file systems in great detail later. But broadly, there will be a pointer to the file system that the process is a part of. It can be part of only a single file system. A process could have opened a bunch of files, so the list of files that it would have opened, that would be there in the task struct. We have discussed what a signal is in various instances, right? Not just one instance, but various instances. So we have said a signal is something that the OS uses to communicate with a process. But how would it do? So in the case of a system call, you have a system call handler. Given the system call, the handler is called, which means the function is called. Similarly, the processes register a signal handler, which is nothing but a signal struct signal, and it essentially encapsulates a function inside the processor's address space. So the moment a signal comes, this function, which is the signal handler, is called. Okay. So the list of all the signal handlers are also stored within the task struct. A few more IO related fields like list of block devices that are used and IO context, which is nothing but the devices that are used and their permissions and so on. All of that information is also there as a part of the process. So the last thing that we would like to add is that so we have broadly looked at what? We have broadly looked at task struct. We have looked at its main fields, and we have seen how they are organized in terms of the data structures. So the kernel also has a lot of support for both debugging processes and debugging itself. So processes, as you have seen, are organized in a child parent hierarchical tree like fashion, right? So one process can pretty much take over another process. This feature is there, which allows, systems like debuggers to execute, where the child would execute, but the parent would be the debugger that is kind of controlling it. So this controllability of processes is there such that you can number one, do debugging. And also you may, if you want to implement a secure sandbox, a sandbox is nothing but a controlled environment where the whatever a process is doing is regulated, which means it can't access resources that it doesn't have permissions to access. So processes activity can be traced as long as the process gives consent to it being traced, right? So it needs to tell the kernel that look, I don't mind if a certain process kind of tracks and traces me. So basically, the parent in this need not be the parent. It could be a separate, it could be a separate process, but it's typically the parent process that observes and controls. So it is giving the parent permission to say that, okay, fine, you can, control me. And this is the ptrace mechanism where in the flags field, we enable the ptrace flag. So basically say that, look, I am willing to be traced, right? So the child process has to indicate to the kernel that, look, I'm willing to be traced, and my parent can track me, right? The parent can be the tracker process, and it can track me, right? Sorry, excuse me. So whenever there is an event of interest, like a fork or a syscall, right? Fork is a type of system call, but any kind of system call. And let's say the parent has told the kernel that, look, now that you have the consent for tracing the child, right? So let us call it the tracked process and the tracker to kind of keep the discussion generic. So since the tracked process has already given its consent and authorized the tracker will say that, look, I'm interested in these events. So if that is the case, that an event of interest comes, then the process that is being traced, that stops, and the tracker or the tracer process, that resumes. Right? How does it resume? So a seek trap signal is sent to it to tell it that, look, something of your interest has come up. If you are interested, take a look. So the signal handler runs, and given the fact that it has the permission, it can inspect the state of the tracked process and modify it also, right? Similar to a debugger. It can inspect the state, it can modify it as well, and basically, you can look deep inside what a program is doing. And in the case of security, if you're running it within a sandbox, then you can see whether certain behaviors are allowed or not from a security standpoint. So this finishes this part of the chapter. So we'll now look at process creation and destruction.